All right, I really wanted to see how that fact would go over in a bar. All right, thanks for coming. Yeah, I don't know if you heard about this. You know, it may have slipped under the radar a little bit. No, seriously. I can't tell you how excited we are that in the couple weeks after the announcement, February 11th, the hashtags LIGO, Gravitational Waves, and Einstein was right were retweeted 70 million times. And we never expected anything like that to happen. But after decades of effort, it's very gratifying to see that much excitement. So what I wanted to do was kind of fill in some of the gaps in the news coverage and answer a lot of the questions we get from people who are excited but aren't really sure why they're excited. They're just kind of black holes, woo! So anyway, so let me start with, all right, I'll do that. What is a gravitational wave? So you've all seen these two-dimensional pictures before of you imagine this elastic sheet and then you put a heavy bowling ball in the middle and space curves down towards the heavy object. Oh, it was off? I am an experimentalist after all. All right. I mean, it's not the greatest picture because, of course, space is not two-dimensional, but it does reinforce the idea that gravity is not heavy objects reaching out and pulling other objects toward them. Gravity is a geometric effect. It is a warping of space so that objects that want to travel in straight lines, well, those straight lines aren't straight anymore, and they naturally want to fall towards the heavy object. In 3 dimensions, what this means is that space stretches and shrinks. The distances between objects will actually change if a heavy object is present. So, to understand what a gravitational wave is, take this picture and take it one step farther. Take the heavy object and move it around. So every time it comes near, space is going to stretch, and then every time it goes away, space is going to snap back again. And if you imagine something moving in kind of a periodic fashion, then space is going to, you know, stretch and go back and stretch and go back. And those changes are going to oscillate and ripple outward as if you were to throw a rock into a pond. That's what a gravitational wave is. Anywhere you have astronomical amounts of mass moving somewhere from point A to point B, it can be 2 stars, neutron stars, black holes catching each other in their mutual gravitational pull and spiraling in until they collide. It can be the core collapse at the center of a supernova. It can be just stars orbiting in place as long as they have a little wobble to them, you know, as long as they're kind of egg-shaped. Anything where mass moves from point A to point B, it's going to create these ripples, and eventually they're going to pass through us and warp the distances between, say, you and I. The only problem is it's frickin' small. Let's imagine the most catastrophic of those events. 2 black holes spiral towards each other and collide. Let's not have it in this galaxy because that would end in tragedy. Let's have it be the next, say, cluster of galaxies over. The size of the effect you would expect from that is the distance between you and I would vibrate back and forth by 1 part in 10 to the 21, 1 followed by 21 zeros, which is a meaninglessly large number. The best analogy I could think of was it's equivalent to the distance between the Earth and the Sun oscillating back and forth by the width of an atom. And again, that's a huge signal, right? If you want to study these things, you need to be able to measure even smaller than that. So I suppose the next most common question I get is how on earth do you measure something that small? Somehow we have to come up with 21 factors of 10. And here's how we're going to do it. We're going to take advantage of a physical property called interference when any two waves are superimposed. If they both crest and fall at the same time, then they are in phase with each other and they'll add together and you'll get an even bigger wave. But if they're out of phase where one rises when the other falls and vice versa, and you move away from and toward the mic, then they're going to cancel each other out and you're going to get no wave at all. So let's take advantage of that. First, I need a wave. So I'm going to take a laser. Aha, laser. It's going to be an infrared laser. It has a wavelength of about a micron, 1/millionth of a meter. So a millionth. That's 6 orders of magnitude. 15 to go. Now, the bigger the amount of space we measure, the bigger the effect. So I'm going to split it, and I'm going to send it down 2 directions as far as the curvature of the Earth will allow before it gets hard to build something straight. That's going to be on the order of 4 kilometers. So the round trip distance is 8 kilometers. Let me round up to 10. 10,000 meters, that's 4 more orders of magnitude. I'm up to 10. Not remotely good enough. So instead of just going down, I'm going to have the light go back and forth several hundred times, bounce, 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 before it finally leaks back out. Round up to 1,000, that's another 3 orders of magnitude. I'm at 13. All I have to do now is tell the difference between in phase and lots of light and out of phase and no light at the output to 1 part in a billion, and I'm good to go. No worries. So that's what we build. This is the actual observatories. There's 2 of them because you want to make sure what you measure is not like someone running their lawnmower nearby, any kind of terrestrial vibration. If you see the same signal in both within the transit time of light from one to the other, you're more confident that it has some astronomical origin. So this one is in Livingston, Louisiana. It's about 20 miles east of Baton Rouge. Worst possible place to possibly put this detector. It's sinking. They're logging the forests nearby. I have no idea. I think it was pork to a congressperson or something. The other one is in southeast Washington State in what's called the Hanford Nuclear Reservation. That's the perfect place because it's a 400 square mile area where the U.S. tests most of its prototype future nuclear reactors, and nobody goes there because there's big Marines with machine guns going, Funny thing, the first time I flew in here, there was a person who lived nearby who was on the plane next to me. She didn't know where I was going. And as we flew over it, and it had just been built, she got real quiet. She leaned into me and went, "You see that? They won't tell us what that is. But we know the truth." As I'm surreptitiously closing my bag so she doesn't see pictures of it inside. No, seriously, what is it? She says, "It's a time machine. You start in the middle and they launch you down to the end. And by the time you get there, you're going fast enough to travel through time." And I said, "That's fascinating. But why is it an L? Why wouldn't it just be a straight line?" And she says, "They have to come back." So, absolutely terrifying. I'd never know how I wasn't abducted that day. But anyway, this was built in 1999. For 17 years, I've been giving talks about someday, maybe, we might just, I finally get to give a talk where I get to show it. All right. What did we see? Well, the interferometers were turned on September 12th, 2015 for an engineering shakedown to get them ready for 4 months of study. Less than 48 hours later, at 5 a.m. on September 14th, when no one was messing with it because it was 5 a.m., this happened. What you're seeing here is called a chirp signal. It's 2 black holes came near each other, mutual gravitational pull, spiraled around, fell toward each other. As they fall toward each other, they spin at a higher rate, kind of like a figure skater pulling their arms into their body. And the amplitude gets bigger too, so it gets higher in frequency and higher in amplitude. It's kind of like a sound that gets higher in pitch and higher in volume. So it sounds a little like whoop, like that. So we call it a chirp signal. And there it is. And we see it in both, clear as day. There's, by the way, 10 to the minus 21, that thing we were aiming at. Clear as day within 7 milliseconds of each other in both detectors. Now, one thing people ask me is, how do you know they were black holes? Well, there's a whole group of people who take the equations of general relativity and they take a whole bunch of, and by a whole bunch I mean about 250,000, different possible masses of the first object, masses of the second, spins, velocities, initial distance apart, and they calculate what they would expect the waveform to look like. And they take each of those 250,000 different waveforms and lay them on top of the data one at a time until they find the one that fits the best, which is this one. How do we know it's accurate? Because this line right here is the subtraction of the data minus the model. Notice the model's not doing anything over here and the noise is about that big. Over here the model is huge and the noise is still about that big. The noise is just noise. There's nothing additional because of a discrepancy between the signal and the model. You see what I mean? That's how we know it's very accurate. So from that model, you can figure out, first of all, the masses of the objects that generated this signal, which turn out to be 29 solar masses and 36 solar masses. Second, from the frequency at which they were orbiting each other, right before they hit, you can figure out how close they were to each other. And it turns out to be about 350 kilometers, or roughly the distance from here to Dallas. This is how we know they were black holes. Regular stars would be too big. They'd never get that close before they merged. Neutron stars are too light. You can't get 29 solar masses in a neutron star. The only object we know of that fits that description is a black hole. So who cares? Why are we interested in this? First of all, there are many models of how the universe evolved that do not allow for black holes of this size outside of the very center of a galaxy. Or if they do allow for them, there's so few of them that the chances of two colliding with each other is essentially nil. Those models must now be modified or discarded, right? Because we've now seen this for the first time. The chirp is easy to calculate, but once the two black holes merge with each other, the dirty little secret of general relativity is, while it is a complete theory, solving it requires a 4x4 matrix of 16 partial differential equations, the solution to each of which depends on the solutions to the other 15. So it's like 16 simultaneous chicken and egg problems, right? General relativity tells you what will happen, and we can never solve it. But now, if you see the chirp, whatever comes after it, that is a direct observation of what general relativity was being mean and not telling you. And so, as is always true in physics, if you want to know what's going on inside of something, smash it into something else. Now, every time two black holes hit, we can figure out what's going on inside of them. And of course, every time you have a new type of telescope, radio waves give you pulsars, cosmic rays give you cosmic microwave background, or microwave, sorry, cosmic microwave background. Well, now, those are all types of light. Now we have something that's just completely perpendicular to that. We have something that's not even light, that we can look at the universe with. Who knows what kind of random objects you're going to find. So the final question is, what now? Oh, we saw one. That's it. Pack it up. We're done. Let's go home. No, that was never the goal, right? I mean, yes, we want to detect one, but ultimately we want to detect lots. Because now this transitions from being a, wouldn't it be cool if it works, to this is now an astronomy experiment. Right? And so, remember, I said this happened in the first 48 hours of the run. It ran for 4 months. That data is still being analyzed. There might be more detections in there. There's totally more detections in there. But I can't tell you anything about it. Don't worry. But anyway, it'll be announced. If we see something else in there, that'll be announced soon. Meanwhile, it's not even within a factor of 3 of its maximum sensitivity. The laser's running at like 1/8 of its maximum power right now as it slowly works its way up to better sensitivity. And there is a growing network of these things. There's the 2 in the US. There's one in Hanover, Germany called GEO. There's one in Italy called Virgo, which we share data with, but which was down at the time this occurred, unfortunately. It will be up this summer. Don't worry. They're building one in Japan underground in a mine shaft inside liquid helium dewars to make it more sensitive. Good luck with that. And in the wake of this detection, they just got funding to build another one in India, which will also be under the LIGO banner. So all those will eventually share data. The more you have, the better you can triangulate where things came from and get to the point where we detect gravitational waves and we say, oh, that looks like a supernova. Hey, Hubble telescope, point that way and wait 6 hours. And then it'll see the supernova from the very beginning. But anyway, I hope that answers how it works, why it's excited, ready to take questions. Thanks for having me today.
All right, I'm so busy eating my dinner, I wasn't ready. Okay, we had a couple questions on Twitter. So first of all, what is the speed of the gravitational waves?
Theoretically, it's the speed of light. That's one of the things we hope to verify, because once you have multiple detectors, you can look at the different arrival times, and you can see if they are all consistent with the speed, with the speed being the speed of light. But theoretically, that's what it should be.
Okay, and the other Twitter question was, why does gravity cause a change in the rate of time?
I mean, how mathy do we want to get today?
I have a simple answer, which is go to our YouTube channel and look up our general relativity talks from November.
Yeah, I mean, so, by the way, you'll notice on my name tag, it's Gravitational Wave Experimentalist. Dirty little secret, not an astronomer. I'm actually a particle physicist who switched fields because he wanted to work on the baddest machine that there was. I'm actually an optics person, right? So when I give these talks, I'm kind of pretending to be an astronomer, you know. Kind of read the papers very closely, but I don't have a good intuitive explanation for like half of general relativity in 2 minutes in a bar, but yeah. If you have questions about the machine, go nuts.
Okay. Any questions about the machine? We've got one at the back over here.
How do we guard against seismic tremors and other sources of vibration?
All right, so the question was, how do you get rid of seismic noise? That's a good question, because it is one of the most limiting things that determines, the three things that really limit us are seismic noise at low frequencies, thermal noise, basically the Brownian motion of the surface of the optics at middle frequencies, and then the laser power at high frequencies. To demonstrate how we deal with seismic noise, to lowest order, we use harmonic oscillators, right? Here is my pendulum. And if I move this at a very low frequency, we all know that the bottom will move just as much as the top. And then as I go to higher and higher frequencies, I'll eventually hit a resonance frequency where all the energy remains and it moves a lot for very little input. What they never teach you in school is what happens if you go to even higher frequencies, right? Like really fast, right? The faster I move the top, the less motion there is on the bottom, because every time it starts to go one way, I'm already pulling in the other. It is pendula and springs. The motion drops as 1 over frequency squared as you get above the resonance. So we take this seismic filtering and we take our optics, we hang them from a pendulum, we put the pendulum frame on a table which sits on a layer of springs, which sits on a table which sits on a layer of springs, which sits on a table which sits on a layer of springs, not even joking, which sits on a table which sits on a layer of springs. And they all have a resonance frequency of around 0.6 to 1 hertz, 1 cycle per second. And then it drops as 1 over f squared to the 5th, because there's 5 of them, so 1 over frequency to the 10th. So at 10 hertz, the motion has been attenuated by a factor of 10 billion. So above a certain frequency, it's as if it's just floating in space. Even that's not a good enough for frickin' Livingston, because again, they're mowing down the trees. So there, you have to do more. You have to actively sense the motion of the ground with seismometers and accelerometers, and then you take what's called a piezoelectric transducer. It's basically a crystal that when you apply a voltage, it will stretch and shrink its own shape. And you take this crystal and you sit a 2-ton optical table on top of it. And you take the seismometer signal and you flip over the sign and you send it, and it will actually lift the table up and down to exactly cancel the motion of the ground as it happens. And so that's how we are able to run even when they're cutting the trees down.
All right, we've got time for one more question, and I see one way up top.
So I assume you're getting tons of signals, and you've got that first signal, but it must be overlaid with a bunch of other signals. How do you separate them all out?
All right, so the question was, first of all, I assume you're getting tons of signals. No, not yet. I mean, again, we wouldn't be that excited about one. Again, I shouldn't actually say anything, but no, we are not awash in signals. They are very, very rare still. I mean, the hope is to eventually be awash in them. So one of the ways you make sure you separate it from the noise is, first of all, you make sure identical signals happen in both detectors within however long it takes for light to get from one detector to the other, which by pure coincidence is 10 milliseconds down to the second decimal place. It wasn't designed that way, it just worked out. Basically you take let me back up a little bit. Dun, dun, dun. Okay. You can take the signal from one device, lay it over the other device, and make sure they actually match. Then what you do is you do many, 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 many millions of possible, unphysically possible combinations. Like you take the data from Hanford.
That's not what I'm asking.
Okay.
What I'm asking is if you have other signals at the same time that are coincident with those signals.
So astronomical signals or cars going by? Oh my God, that'd be amazing. That is a problem we would love to have. This represents the only signal detected in the first 16 days of operation. We will likely never get to the point that there's that much happening, solely because the frequencies at which we're sensitive are just the frequencies where stars go to die. Right? The stars spiral around each other, and then in their last seconds of life, when they crash into each other, that's what we can see. So people often ask, well, why don't you launch this into space, and then seismic noise isn't a problem? And that's true. Your problem is solved, and then your problem happens. Because then you're sensitive to thousands of stars all over the place while they're spiraling around each other. And you have thousands of signals, all different amplitudes, all different frequencies at the same time. That's called static. Right? How do you tell them apart? I'm describing, by the way, an experiment called LISA, the Laser Interferometer Space Antenna. The way they intend to tell multiple signals apart is by introducing periodicities. The spacecraft that make up the thing will tumble. They form a triangle that will rotate. That rotating triangle will also precess, and then it will orbit not the Earth, but the Sun trailing behind the Earth, and it will wobble. And so all those different wobbles, depending on which direction the signal is coming from, will cause wobbles in the data at different phases, and that's how you disentangle it. But it's hard. I mean, it's one of the reasons this experiment doesn't exist yet, is because the people who work on it every few months will have what they call a mock data challenge, where someone will just smash 4,000 sine waves together and say, go. And they have to come up with algorithms to tell them apart.
All right, we have to move on, so let's say thank you very much to our Nullifier of Noise.